It's a great pleasure to present on this topic. Many people contributed to the materials which will be presented in this talk, and most of them are here, and I'll be calling on some of them to answer some of your hard questions. I hope that you do ask hard questions both during the talk and at the end of the talk. So this is an outline. I will start by discussing the observational and theoretical facts about neutron stars, about pulsars and magnetars. There are many old puzzles, so it's not just the new data that has come in over the past few years about fast radio bursts and things like this that Roger mentioned. But in this field, there are old puzzles which have been with us ever since the discovery of pulsars in 1967. And so I'll briefly outline what these old puzzles are, and then I'll discuss what I consider to be the discoveries that were made within the collaboration on theoretical research pertaining to these old puzzles. So the connections will become apparent. And then I will also spend some time talking about new directions. I will describe a couple of these new things that we are thinking about and perhaps take some ideas from the audience. All right, so just briefly, pulsars are rotating neutron stars with a beam attached to them. The radius of a pulsar is about 10 kilometers, and the densities are incredibly high. At the core, the densities reach something like 10 to the 15 grams per centimeter cubed. And we now, one of the fastest pulsar known was measured by Jason Hessel's and Vicky Caspi's group already quite a bit of time ago, and it's spinning with a rotational frequency of 716 hertz. At this rotational frequency, if you take a point on the equator of the pulsar, it's moving with the speed of about 1/5 of the speed of light. So these are extreme objects. They contain a lot of rotational energy, and we see this rotational energy being tapped in astrophysics. So in this picture, you see two famous pulsar wind nebulae, and what happens here is that the rotational energy of the neutron star through magnetic stresses get transmitted into the magnetized wind. This magnetized wind, as it goes, runs into this nebulae and powers the emission of this bright nebulae. So we can do colorimetry of this, and we see that substantial rotational energy of this pulsars has to be lost. And in fact, very soon after the discovery of pulsars, people have measured the slowdown of this neutron star. So this is the first measurement in 1968. And you can see that the period is increasing linearly with time. On the y-axis, the units are 10 to the minus 7 seconds. So already back then, you can see how precise the measurements of the rotational periods on the neutron stars were. OK, so the theoretical picture of why this slowdown happens has been worked out by generations of previous generations of theorists. Anatoly did some groundbreaking work on modeling this in force-free electrodynamics in 2006, but already Goldreich and Julian realized in 1969 that most of the emission, actually all of the energy and angular momentum lost from the pulsar has to go out in magnetized wind. Okay, so this is something that has been known for a while. And so the theoretical prediction is quite firm that if the magnetosphere of these pulsars, if the magnetic fields in these pulsars are stable, if they don't move in the frame which is rotating with the pulsar, then the torque is such that omega dot is minus k omega to the power n, where n equals 3. So this is a firm prediction of theory for stable magnetospheres. This is well understood. And as I'm going to argue, this is not what we see in observations. Okay, so there's significant deviations from this picture of a stable magnetosphere driving steady wind. Okay, now because of this work, we can get an estimate of the dipole component of the magnetic field. So most of the taxonomy of pulsars is classification in so-called PP dot diagrams. So this is the period on the x-axis and the period derivative with respect to time on the y-axis. And you see several clusters of pulsars, of neutron stars on this diagram. The main cluster is this one. So this is the garden variety, most numerous ordinary pulsars. So these are typically quite young objects. They have fields of something like 10 to the 12 Gauss, and rotational periods sort of clustered around the second. Then there is an ultramagnetized class here, which are called magnetars. They have dipole components of the fields of a few times 10 to the 14, up to 10 to the 15, and perhaps the multipolar internal fields, which are much stronger than that in the interiors of the star. And then in the left corner, we have millisecond pulsars. They're very rapidly spinning. They're very old objects, typically members of binaries, not all, but we think that all of them perhaps were members of binaries in the past. And it's the accretion from the companion which both spins these stars up and also makes the magnetic field of these neutron stars to be extremely weak, 10 to the 8 Gauss, weak by the neutron star standards. And you have heard about pulsar timing arrays. So pulsar timing arrays are using these pulsars because they have exceptionally regular timing properties. Now, in this talk, I will mostly be talking about the mainstream pulsars and magnetars, but towards the very end, I'll also mention the millisecond pulsars. As I said, the rotational period of these pulsars is increasing with time, and there are good explanations for this. But pretty quickly, it was realized that this is not always the case. And in fact, in 1969, 2 years after the discovery of the first pulsar, Radhakrishnan in Manchester have measured a dramatic increase in the rotational frequency of the Vela pulsar. So here is the period measurements, and then there is a jump of 200 nanoseconds or so, and then the track continues with this new initial conditions. So this dramatic increases in rotational frequency are referred to as glitches. And if you look at Vela in particular, Vela is glitching quite regularly, about once per 3 years. We're lucky enough to have a glitch from Vela. Other pulsars are glitching much less regularly. But by now, we have the benefit of a very long baseline, over 50 years of pulsar observation, so we can collect the statistics of these glitches. And so it was realized, about a decade ago, that the distribution of these glitches is very, very broad. So this is delta nu over nu in units of 10 to the minus 9. Okay, nu is the rotational frequency of a pulsar. And you can see that this goes over almost 10 orders of magnitude, 8 orders of magnitude in magnitude of these glitches. And this distribution is bimodal. So there is a lot of phenomenology. If one creates the complete theory of glitches, there is a lot of phenomenology that needs to be explained. But as I will argue to you, we don't understand glitches even to zeroth order. So there is, before creating a comprehensive theory, we have to understand something about the glitches. So this is what some of my talk will be about. There is also other puzzling things. On top of glitches, these breaking indices, right? Remember, omega dot is minus omega to the power n. If you measure this n for middle-aged pulsars, they all have midlife crisis. They seem to have these n's all over the place. So there is clearly very substantial long-term deviation from the steady magnetosphere approximation. On top of it, there is so-called timing noise. This is of great interest to people who do pulsar timing arrays because this interferes with the measurements of gravitational waves. But it's especially pronounced in young pulsars. And you see these correlated variations between the torques exerted in these pulsars and the changes in their pulse shapes. And some of these correlations have this kind of quasi-periodicities, which are very puzzling. And the typical time scales here are, a few years. So this is very puzzling from the point of view of magnetosphere, where the time scales are supposed to be much shorter. So I would say there are no good theories of this timing noise at this time. And in fact, in my talk, I will not be addressing it unless you ask me questions. I can share some ideas. But this is very puzzling and very prominent pulsar phenomenology. Magnetars came into play. In our collaboration, Chris Thompson was one of the pioneers of the notion of magnetars. These are neutron stars which have extremely strong magnetic fields. They are now in the mainstream of astrophysics. I'm going to address or mention one aspect of magnetar phenomenology. So originally, when people started talking about magnetars, observationally, it was either in the context of flares. Some of the neutron stars were showing flares. So these are so-called soft gamma repeaters. Or they were showing anomalously high X-ray luminosity, which was clearly powered by internal magnetic fields. So these were called anomalous X-ray pulsars. It was realized later on that on top of the flares and just high persistent luminosity, magnetars are transient objects. Many of them are transient objects on much longer time scale, on a time scale of a few months to years, and they go into this so-called outburst. So here is the X-ray luminosity of magnetar as a function of time, one of the first outbursts that were discovered. You see this bright, increase in luminosity, which can be up to a factor of order of 1,000, okay? And then there is like several months to years decay. And sometimes, this is a simple outburst. And sometimes these outbursts have, complicated morphology. Also, the pulse shapes in magnetars are very variable. So it's clear that the magnetosphere in the magnetar is extremely lively. It's breathing and moving. So this is, this is the example of how the pulse shape changes in all bands on a time scale of about half a year. You can see the pulse shape of this magnetar, this particular magnetar there, changing very quickly. So clearly something is moving these field lines. Now for this outburst, the theoretical picture is that this outburst of phenomenology is well explained by some twist which is imparted into the magnetosphere on a fairly rapid timescale. This was worked out by Andrei Beloborodov in 2013, building on the work by Thompson, Maxim Lutikov, and Sri Kulkarni a decade earlier. So the question for the interiors is, how do you impart this twist so rapidly from the interior into the magnetosphere? So again, the time scales is of order of several months. You need to do it quite rapidly. Okay, you need to do it quite rapidly because otherwise the resistive currents in the twist would untwist it if you do it very slowly. But at the same time, it's not a flare. It's not a very rapid second event. So the implicated physics is some kind of triggered plastic flow in the crust of a magnetar. The nature of this plasticity needs to be understood. The microphysics of these plastic flows needs to be understood from the first principles. Okay, so this is the theorist picture of the neutron star looks like. Going in from outside in, you have magnetosphere, which is filled with pair plasma. Something sometimes happens in this magnetosphere. I'm going to leave magnetosphere to Anatoly and Chris and other people, so I'm not going to talk about the magnetosphere at all. My topic is the crust, which is the outer kilometer of a neutron star, which has a combination of a crystal lattice and also superfluid neutrons, which are coexisting at the same location as a crystal lattice. So extremely unusual environment, very difficult to reproduce something like this in laboratory, in terrestrial laboratory. But nonetheless, this is the physics which is very crucial. And then you have a liquid core, which is clearly a soup of neutron fluids, which are likely a superfluid, protons, which are about 5 to 10% of mass, is in protons, proton fluid, which is likely a superconductor, and an extremely degenerate gas of electrons. Okay, so this is the composition, conventional composition. Now, in the very, very interior, we don't actually know. We don't have enough theoretical power, theoretical understanding to say whether this continues to be neutrons and protons and electrons, or whether something more exotic happens there, like quark phase. So I'm going to briefly mention what our collaboration is thinking about, the case that maybe the center of this core, there is some unusual quark phase with some unusual electromagnetic properties. So I want to now talk a little bit about dispersal glitches. And there is a wonderful one-page Nature paper by Anderson and Ito, written in 1975. And I have a quote from the abstract, which I really like, that the macro glitches, especially those in the Wheeler pulsar, may be caused by catastrophic release of pinned vorticity. Beautiful sentence. So what does it mean? So these people realized, already knew from the work of earlier theorists, that there's going to be superfluid in the crust of a neutron star. And what is a superfluid? Just briefly to mention, superfluid is something that has no viscosity, and rotating superfluid does it by forming an array of dense vortices. Each vortex carries a quantum of circulation, h bar over m, where m is the mass of the particle. Now, the circulation is completely fixed so long as you fix the location of the vortices. So look at my pointer. This is a vortex. I fix its location. It creates a circulation. This circulation is fixed. If you manage to fix all the vortices inside the crust of a neutron star, the superfluid flow is fixed. It cannot change, no matter what happens to the rest of the star. So Anderson and Ito realized that if there is an effective pinning of these superfluid vortices to the crystal lattice or other things, this spinning would fix the superfluid velocity, and even though the rest of the star spins down, the superfluid keeps rotating at its original angular velocity. So this motivates this cartoon picture of glitches. So here is time, here is angular velocity of the rest of the star, which is connected to magnetic fields, radio beams, whatever. Okay, this is the blue thing. And then the superfluid is the red thing. As the rest of the star spins down, the superfluid rotates at a fixed angular velocity. And then the glitch is when it all breaks down. Okay, glitch is a moment where this differential rotation between the superfluid and the rest of the star can no longer be maintained. So obviously, there is some stress which has to build up. When this is no longer maintained, they start talking to each other and they exchange angular momentum. The superfluid spins down. You, of course, don't see this. The rest of the star spins up. And then you see this because the rotational frequency of the star increases. The origin of the stress is the Magnus force. So let me just quickly say that if there is this is the superfluid vortex when you look at it from above. And with this vector, I show the velocity of the superfluid relative to this vortex. Mr. Magnus understood that there is a lift which acts on any kind of rotating object immersed in aerodynamic flow. And the superfluid vortex is no exception because it creates its own circulation in this way. If the superfluid relative to the vortex moves in this way, it experiences a perpendicular lift, which is called the Magnus force. The expression for this I have written down here. And this Magnus force, if the vortex is spinned, it has to be compensated by the spinning potential. Okay? So as you build up the differential rotation, this force builds up, and then the pinning potential is not enough to hold this vortex, so it starts moving, and this is the glitch. Okay? This is the cartoon. Now, the basic physics, okay, you can immediately start asking, well, of course, you don't have one of these vortices. You have about 10 to the 17 of these vortices in the neutron star interior. So the question you should be asking, okay, this is a picture for a single vortex, and now I'm going to tell you some numbers. The typical distance between these vortices is something like 10 to the minus 2 centimeters. The typical distance between the pinning sides, this is a crystal lattice, is something like 10 to the minus 11 centimeters, so 9 orders of magnitude different, okay? So each vortex lives in its own environment and its own pinned potential, and basically, this vortex is somewhere at Jupiter. It doesn't know about it. Jupiter, I mean, if I take 1 centimeter here and take, 10 to the 9 orders of magnitude more, you get somewhere in that neighborhood. So these vortices normally don't talk to each other, okay? Because there are so many of these vortices, the vortex feels its own mean flow and the pinning forces, but it's basically disconnected from its neighbors. So what is the origin of this amazing coherence that you need to generate a glitch? Right? For a glitch, you need something like 10 to the 11 of these vortices moved by tens of meters, okay? Just think about the scale disparity here. So it's a huge scale problem, and it's a huge coherence problem. And so when we started thinking about this, we decided, okay, this is too hard. We need to go back to the microphysics of how these vortices individual lives, okay? Before you can understand their collective behavior, you have to address its own private life of these vortices, and then maybe we can get an insight into their collective behavior. So it turns out that by going back to their private lives, we got some insight of what can generate the collective behavior of these vortices. So, okay, this is just some equations. So it's not all completely empty. So equations of motion of this vortex has the Magnus force, has a pinned potential, it has the tension, and it has the friction. In the original paper, which was written by Bennett Link and myself, we had this friction as a phenomenological term, but we already made an interesting discovery of a hysteresis in that paper, which we think is the cornerstone of all the glitch physics, okay? And then with Xin Chang, who is a graduate student with important collaborators that I'll list later, we actually obviated the need for this friction force. We replaced the fixed lattice with molecular dynamic simulation of a lattice. And then this friction arises naturally between the exchange of energy of the vortex motion and the phonons, the shear phonons in the lattice of the crust. So let me just show you one simulation from this paper, okay? And so what we did in this simulation, let me just tell you, first of all, what happens, and I'll play the movie. Here, you will see this vertical bar is what this background velocity is, and you'll see this vertical bar moving to the right, and the vortex, which is in blue, after some initial adjustment, remains pinned, okay? And then once you reach some critical velocity, it unpins, and then what we do is we gradually reduce the background velocity back to 0, and we notice that because of all the perturbations, all the Kelvin waves which propagate along this vortex, it remains unpinned until much lower background velocity. So now I'm going to play the movie. You will see these things. So some adjustment initially. This is the view from the side and also the view from above. XY is from above. The other one is the view from the side. It remains pinned. It's about to unpin at some critical velocity. Now it's unpinned. It moves. Okay, and we now reduce back the background velocity. It remains unpinned. The Kelvin waves, all those wiggles which propagate along the vortex. This is the Kelvin waves. And then at much lower background velocity, it repeats. So there is a hysteresis, right? This hysteresis is very important. Okay, I don't want to play it again. What causes the pinning is the interaction of the vortex with the lattice, the crystal lattice. So it's the interaction between the circulation of the vortex and the cluster of neutron liquid which sits inside the nucleus. Okay? So this is just to say that this unpinning process, it causes Kelvin waves. These are the helical waves which propagate along the vortex. And this is quite robust. So in particular, if you have two different grains in the crystal which are differently oriented, this unpinning wave can cross from one grain to another. So you can see in this experiment, the unpinning will happen in the less pinned thing, and then the Kelvin waves propagate and it unpins in the upper layers. And we find that this is quite robust. So this kind of unzipping line goes along the vortex. So this hysteresis, it gives us an idea that maybe if you have maybe a glitch is not when all the vortices at the same time reach this unpinning velocity mysteriously, but maybe they're sitting here at the lower branch, and then there is some event which takes these vortices and gives them enough kick to be in the upper branch, which is unstable. So perhaps there is some event which kicks from lower branch to upper branch, and we considered two possible things. One thing is a quake. So what we do now is we take this lattice and we shear it, and you'll see the shear layer forming, and this unpins the vortex, and then you'll see the shear layer healing, but the vortex remains unpinned. So this is a simulation. The shear layer is about to form. The vortex is unpinned, so the movie accelerates a little bit because it's kind of boring. And then we stop shearing, the lattice heals. You see the lattice healing soon, but the vortex remains unpinned. It's in the upper branch. So it works. In the case of a quake, it works. And then you can think about the global picture, right? If you have a slip plane, so all the vortices which are crossing the slip lane caused by the quake, they all unpin, and because of the Kelvin waves propagating along this vortex. So in the end, you unpin the macroscopic part of pinned vorticity in the language of Anderson and Ito. So the second idea that we considered is that perhaps even though these vortices typically are far away from each other, but they're lines, and lines moving in space intersect at subpoints. So we were curious what happens near those intersections. And so here is a simulation of what happens near those intersections. One vortex gets unpinned, approaches the red vortex, which is pinned quite well, and then their mutual interaction via their mutual Magnus force. Now, near the intersection, of course, the Magnus force is strong. It unpins the red vortex. So we think that this is, these two things can potentially explain the incredible coherence of the glitches, but clearly a lot more work needs to be done. And I just want to mention that there is another way by which the vortices can move, is if the lattice has finite temperature, they can actually, instead of doing this catastrophic unpinning thing, the vortex can creep thermally under the action of a lattice force by making transitions between neighboring pinned states. So this is for the first time simulated in this work by Bennett and myself. And so, sorry, this is some glitch in the, let me play this again. Okay, you will see the view of vortex creeping thermally from above. And so this, now I'll play the side view. Oops. Yeah, it slowly jumps between neighboring pin states. So it's a different way of moving. So, it's complicated. You have to sort out in which case it gets unpinned catastrophically, in which case it creeps thermally. Perhaps most of the time it creeps thermally. There is some difficulty in making a background model. A couple of years ago, we made a simplified model of the creep, and we realized that the global background state is going to be a so-called superfluid river. So if it's steady, it looks like nothing. But if there are some kind of waves and variations in the thermal creep, that maybe this is something like timing noise, exactly. So, this is something that needs to be understood. Now, this is the pulsar which is spun down, and what's shown are the vortices. You see the vortices now begin to reconnect, and they form this region of extremely high velocity inside these loops, right? Inside these loops, you have a river, which is here. This is just a model. It's a simple model. It's probably wrong, but I'm just saying that the background state of this vortex array can have very non-trivial geometry and topology. This is something that needs to be sorted out. Okay. So this is just a poloidal section of the neutron star, and each vortex in this simple model, the vortices are assumed to be poloidal. We now know from the work on thermal creep, the detailed modeling, we know that this cannot be true because the vortices also creep significantly in the direction of the superfluid flow. So the actual picture would be more complicated. But this is just a simple model to tell you that this can be quite complicated thing.
So there is right in this model a symmetry direction.
There is what?
Symmetry direction.
Symmetry direction.
Perpendicular to the plane.
Perpendicular to the plane is the azimuthal direction. Okay, so perpendicular to the plane is the azimuth. It's an axisymmetric model. So it's complicated, and there is a lot of things that need to be sorted out. Now I want to talk a little bit about these quakes. What could cause the quakes in a neutron star? We know that in magnetars, almost certainly the field is strong enough to cause the crust to yield, to cause the crust to develop some sort of slip planes. But normal pulsars, they have magnetic fields which are much weaker. So if magnetic stress is to cause the quake, you need a major perturbation to the magnetic field. I now want to talk a little bit about the giant Hall waves. This is something that we discovered in Powan's language. This is something that we didn't expect to discover. Neither, by the way, did we expect to discover the hysteresis. Okay, this is something that was not expected. Giant Hall waves is an unexpected discovery as well. Just came from, thinking one afternoon. Basically, so let me just say a few words about how the field evolves in the crust. This is an evolution equation. So what I have here is a magnetic diffusive term. This is basically the Ohm's resistivity. But what's unusual about the neutron star crust is that the field is advected by electrons, okay, the electron velocity flow. And so the field is advected by currents. This electron velocity flow can be caused by the actual motion of the crust as a whole, and actually also can be caused by the currents, by Ampere's law. So you have an evolution equation. The time scales for the whole drift depend on the wavelength, can be from years to mega years. But the crucial thing happens in this story is when you have a transition in the core from a normal magnetic field to a superconducting magnetic field. So what I have here is a picture of the crust-core interface, and you see that the magnetic field bunches into the flux tubes. Each of the flux tube carries the critical field of a few times 10 to the 15 Gauss. Between the flux tubes, the field is 0. This creates a huge enhancement in the average tension of the field, okay, in the Maxwell stress. Because remember, Maxwell stress is proportional to B squared. If you average B squared, the field is bunched in this way, you have an enhancement of a factor of 1,000 in tension for the field of 10 to the 12 Gauss. So if you now consider a crust-core interface, it was realized by two smart people, Aggun and Ira Wasserman, who I believe is here. Ira? Okay, great. It was realized that the Maxwell stress has to be tangential across the crust-core interface. But because the stress is so much stronger here, so if you have a mean field which is inclined in this way, the field lines have to basically try to break at the crust-core interface and consider and continue in a very inclined fashion. And this creates a very strong current layer at the crust-core interface. So our contribution was to realize that this strong current will be a source of a Hall wave. And so Ashley made the model numerical model of what this whole wave would look like. So here is the B phi, a picture of the B phi. And you see that this whole wave is quite dramatic amplitude. The field lines actually move a lot in the magnetosphere. And we think that this is the origin of the variability of torque on those long time scales, this whole wave. So this is a slightly more complicated model where the field topology is not as simple. And the field lines are assumed to be advected by neutron vortices, like Ruderman believed. So in this case, what also happens is that the perturbations are so strong that they can create significant magnetic deformations. Deformations here are shown to be of order of a few percent. Okay, this is the strain, can reach a few percent. And this is perhaps enough to break the crust, at least in some locations. So this is the plot of the breaking indices for a particular simulation. You see this breaking index is about 3 when the pulsar is young, but when the pulsar reaches a middle age, it has a midlife crisis, the breaking index goes for a walk. Actually, it's kind of a mad random walk. So, so we think it basically looks like reality in some sense. If you talk about the elastic stress, this is the plot of the maximum elastic stress which is reached in the simulation. Sorry, this is strain, not stress, the deformation. And we see that in some locations it reaches a few percent. So perhaps this is how occasionally you have slips and quakes and you generate glitches in this way. This has actually been modeled by direct simulations, molecular dynamics simulations, the quake. So what you have in this simulation is you will see this magnetic field lines deform. This is kind of a source. This is an input into the simulation, the change of the field line configurations. And you will see in response to the growing magnetic stress, the crust actually breaks, or it forms a kind of network of folds. And it's a beautiful picture. See how it emerges. This is the emergence of all the fault lines and different grains, different orientations. I was watching this. This is not my work. This is the work of Nathan Smith, Matt Kaplan, and Ashley Bransgrove. And I was just like watching it when I was preparing for this talk. It was beautiful simulation. So this is the image. And they actually had to develop a new code which incorporated magnetic fields, peak style. So this is the computation. The particles, the molecules in this molecular dynamical simulations, they're also sources of magnetic, they're also sources of field. So this is directly incorporated, okay? And I couldn't help thinking about the paper that Maxime and I wrote in 2012, where we we made an argument for the amount of seismic energy which would be released in this type of events. And so this is something that I think this team has to do, is to compare and compute the seismic energy. In our estimation, it wasn't going to be very big. Okay, now I want to switch and talk a little bit for the past 5 minutes or so of my talk. I want to talk about magnetars. So this is not the normal pulsars, but extremely strong magnetic fields. And there are two effects that our collaboration has considered, two new effects. One of them is the effect of Landau quantization of the electron levels in the crust. This is the work done by Peter Rao in collaboration with Ira. And what these guys have realized is that there is an extra term, and this term, because of this is called the de Haas-van Alphen oscillation in conductivity. Okay, so as you changing magnetic field from a place to place, the whole conductivity has very short wavelength variations. And this affects the whole dynamics in such a way that it increases the whole turbulence. So Peter now has developed his own thermomagnetic code, which is basically reproducing the results of José Pons and other Europeans in terms of thermomagnetic evolution, but now also includes the effect of this Landau quantization, which drives small-scale structure. You can particularly see it in this couple of simulations where this is without quantization, this is with quantization. You see how much more small-scale structure you have here in the current. Now, the detailed model also shows that this doesn't change very much the thermal luminosity, even though you have enhanced dissipation of magnetic field. It doesn't substantially change the thermal luminosity of this neutron star. This is because all of this interesting dynamics happens in the region where neutrino emission is very high. So even though you have a lot more dissipation, it quickly is radiated in neutrinos and not much reaches the surface. However, I think it's very promising, and this is still being investigated, this would change, first of all, the overall dissipation of magnetic field, and second of all, I'm convinced that this would increase the elastic stress. The introduction of these small-scale features in magnetic field lines, it will increase the elastic stress exerted by the field onto the crust, and this is still the future work. And the second effect that I want to mention is if you have a very strong field, so of course people, well, not of course, but people have talked about ambipolar diffusion of magnetic field lines through the core. This is the work which goes back to Goldreich and Reisenegger in 1992. And the idea is that magnetic stresses can push the charged fluid, protons and neutrons, protons and electrons relative to the neutrons. And because of this diffusion, the field evolves in the core. What we have considered is whether for extra strong magnetic fields of order of 10 to the 16 Gauss, this is the effect that can also happen in the crust, because the crust also has a mixture of a superfluid, which has no viscosity relative to the charged component, and it has a lattice, but at this magnetic stresses, the lattice structure itself is not very important. So you can, in some sense, heuristically consider this lattice as a liquid. So it's a bit of a leap, but we have written some equations which describe phenomenologically what this evolution could be. And within these equations, we get this magnetic eruption. So where you start with some strong field in the interior, and then you have an eruption. The magnetic stresses propagate all the way to the surface, and they cause an eruption from the surface. So you saw this plume. This is a baryonic plume. So even though the equations are, how can I say, they have some assumptions, but these equations are solved exactly, and they're solved very well. I know I have 2 minutes, right, to talk? That's right. Okay. So, okay. Giant flares produce baryonic eruptions, and nobody understands them. This is one of the ways in which the baryonic eruption could be produced, basically generated by the interior stresses coming to the surface and causing an ejection of matter from the surface in this way. So this class of scenarios, I think, should be investigated. Finally, I want to talk a couple of minutes about the future work. So we had this very nice talk by Mark Alford, which convinced us that electromagnetic properties of quark cores should be very different from normal matter. And so in particular, he educated us about this color flavor locked state that the quark core can reach inside the neutron star. And one of the features in this quark color flavor locked state is that this becomes a dielectric, okay, from the point of view of magnetic field. So you have like this weird thing that you have a superconductor in the outer core. You have basically a dielectric in the inner core as far as normal magnetic field is concerned. And so we are thinking about what will happen in this case with flux tubes. And the natural outcome of this is that the flux tubes will be attached, obviously, to the crust core interface. but also some flux tubes will be attached to this dielectric superconductor interface. The rest of the flux tubes will be ejected by the processes that I described, but these ones, remain attached in this way. So we are thinking about how this configuration evolves. We think that these flux tubes will look like a hedgehog. They will stretch radially between the inner core and the outer core. And they will also evolve slowly. So these radial flux tubes, they will slowly be moving. We think that it will be similar to how black holes evolved. This is the field which was pioneered by Maxim some time ago, and then the beautiful simulations also by Ashley and Bart and Sasha. So we think that very similarly to this, these flux tubes will be moving to the configurations where you have approaching flux tubes of positive radial B field and negative radial B field, and they'll start reconnecting. So we have reconnection sheets. But these are weird reconnection sheets. These are reconnection sheets between quantum flux tubes. So it's probably a little different from plasma physics, but also probably quite wonderful. This is something that needs to be investigated. And the final thing that I want to mention that we are working on is this old puzzle about the magnetic fields of millisecond pulses. Remember I said that they have very low magnetic fields. So how do you get from the pulsars which are here, the mainstream, how do you get by accretion into the lower field pulsars? There are many papers. The classic paper was written by Ellen some time ago, but she hasn't solved the problem, okay? And other people also haven't solved the problem. We think we have some ideas. In particular, I think that the Meissner effect has to be taken into account in the correct way. And will dramatically change the calculations that people have done before. Chris and some friends are thinking about also what happens to the magnetic field, which is advected from the accretion disk, which is going to be stochastic, or generated during type 1 nuclear explosions, nuclear hurricanes during type 1 bursts on surfaces of neutron stars. So this is, whether you can import the field into the crust as a result of the accretion process is an interesting question, okay? So I am done. I want to make conclusions that there are many old puzzles. So when people ask, what is the new data that is driving the necessity for this collaboration? It's not just the new data. These are old puzzles, old things which have been with us since discovery of pulsars. And I think by being methodical and going to the first principles simulations, we can uncover some of this. Obviously, a lot of work still needs to be done. The problems are old, so the solutions will take a while as well. But I think there are new numerical tools and also some new ideas which have arisen as a result. We have had wonderful crosstalks between different institutions. The fact that we were smart enough to invite Matt Kaplan from Illinois State, which brought the whole, machinery of molecular dynamics simulation. This is just priceless. And I think it has energized also, people in different institutions, people at Columbia. Xinsheng is a graduate student that collaborates with Matt extensively. The fact that Ashley in Princeton and other places, and also I haven't had time to talk about this, but people in Tel Aviv and people in Wisconsin are now interested in this class of problems as well, and they have projects which are not mature enough to report here, but are maturing, let me put it this way. And I went here.